Okay, so good afternoon.
Good
You are
afternoon.
this class, which is Solid State Physics 2. So my name is Dr. Adetunji. I work at Best University of Technology Ota as a physicist. I'm a condensed matter physicist. So in this course, we are going to be learning some basic concept about solids that has to do with their applications. So things industrialists, eh, engineers are interested in solid materials before they can use them in industry. So one of the important thing there is what we know as dielectric properties of solid. So this course we are going to be doing it on Fridays by 4 to 5 p.m. Hopefully, like we started today. So if you look at the objective, this is the work plan. And if you look at the objective, I have said that you are going to look at the dielectric properties of solid, then local electric field. We define dielectric constant, polarizability, and susceptibility. We try to understand what magnetization are and what is magnetic properties of some of the materials that we have around and series different types of magnetic materials that we have. We also try to differentiate between some definition in magnetization. For example, what do we mean by magnetism and paramagnetism? Also ferromagnetism and antiferromagnetism. All these things are properties of magnetic materials. Some materials are ferromagnetic in nature, while some are antiferromagnetic in nature. So when you say a magnetic is ferromagnetic, that shows that all the spin of the materials are facing one direction. But when you have antiferromagnetic, they are like a pair. You know, in Pauli exclusive principle in chemistry, you have up spin and down spin. That is how the properties of antiferromagnetics looks like. So the first week of the course, which is today, we are going to be looking at the course guide together. And also, if you have questions, you can ask. Then we try to also check one or two things. In the second week, which mainly where the class will start fully. We look at the first thing we are going to look at is dielectric properties of solid. And specifically, we are going to look at what dielectric properties are and also try to move a bit to look at the local electric field. So in the third week of the class, we'll be looking at dielectric constant, polarizability, and also the dipolarization and dielectric losses. While in the fourth week of the class, we shall be discussing mainly what is magnetism. So there we'll be looking at magnetization, diamagnetism, paramagnetism, ferromagnetism. I will discuss all this in details. Likewise, in the fifth week, we extend the discussion on ferromagnetism also to the fifth week because of what is involved in the course materials. So we'll be looking at antiferromagnetism and antiferromagnetism. While in the sixth week, we shall be looking at magnetic resonance. Here we are going to be talking about some of the techniques used in dictating magnetic properties of materials. So one of them is magnetic resonance. We also have ferromagnetic resonance and antiferromagnetic resonance. All these things, we shall look into details and try to understand one or two things and how possible we can use them to determine properties, magnetic properties of materials. While in the seventh week, we shall be looking at what is meant by imperfections in solid. No, solid materials, they are just like a crystalline materials. Solids, if you, for example, now, if you look at building in the house, you see that blocks are arranged in a form of array. They lay them side by side. That is how crystals are. They are just like that. They are in form of an array. So if you now distort them, let's say for example now, we remove one block from a building, we have created what we call imperfection. And that can drastically affect the structure of the building. The same thing happens in solid. If you create what we call point defect, that is, you just remove an atom or an element from a position of array, then you have created a problem, and that problem is called a point defect. That little things can affect the properties of materials. So also we look at linear defect and the planar and volume defects. All these things we shall discuss them in details in the seventh week. Possibly, if you are able to finish it in the seventh week, It'd be good for us. Then in the 8th week, we do a kind of a revision of what we have discussed so far. So the module and operandi of this we are going to use in taking this course is that how we'll be sending in PDF files, slides rather, for the courses, and at the same time, I'll be sending in short videos in where I will have discussed some of the concepts before the next class, so that in the next class, by the time we are meeting, we just go over. If you have any question, you can ask things you learn from the video, and if you are not really sure of what you pick from the video, you cannot ask me in the live session. So in the process, we'll be able to clear all these things. So one thing you have in mind is that the course consists of about one module, and the module is divided into three. So you have just only one module, but it is divided into what? Three.
3.
Yes, in 3 units. It is one module, but we have 3 units. Do you have the course material? Because I posted it. Did you downloaded it?
Yes, I have the course material too.
Good. So I'll be going to the course material now. Then we'll look at it together and be able to understand what are there in the course material for us to discuss in the next 8 weeks. So this is the course material. So let me go down a bit. So you can see here the study unit. So it has just one module and 3 units. So the first unit has to do with dielectric properties of solid, while the second one has to do with magnetism, and the last one has to do with imperfection in solid. So if we go through the content very well, we will see that in the module 1, where we are going to be discussing dielectric properties, the dielectric properties has series of divisions. We have dielectric properties, local electric field, dielectric constant, polarizability, dipolarization, and dielectric losses. So there is introduction for the course, so which I believe you can read. Then we have a bit of discussions about the dielectric properties, the definitions, and how it is in non-conducting material and also in conducting materials. So all these things are things we are familiar with. Since we are all physicists, at least I believe you have studied physics in year 1, year 2, year 3. So
Yes, sir.
to the best of my knowledge, I believe that most of these things I'm talking about dielectric materials are not new to you, because in year 1, you'll have been told the dielectric phenomenon in material. If you have two parallel plates, capacitor, so the dielectric, the distance between them, you can compute the dielectric. So it's just a bit of a kind of an advanced discussion in this area. But in this period of time, it's going to be related to materials, because uh, we all know what it calls silicon. It's an element in the periodic table. And silicon is one of the important materials used in industry for production of electronic gadgets. And most of these electronic gadgets that we use and are produced based on silicon materials, the properties they use are the dielectric properties of silicon. So ability to try to improve these properties are things that makes us to have all these small food. You know, in the olden days, in the 80s, in the 90s, some of us that grew up during that time, in our houses, we have tube television with long back. But these days, our children are used to flat screens
Yes, sir.
and colored. In our days, it is black and white. It is because ability to tune the properties of material to be able to produce different things. That is what is leading to all these things. You are familiar with most of the torchlight we are using these days. Most of the torchlights we are using these days are purely made from light emitting diode. And this light emitting diode consume less power compared to what we use in those days, that we use torchlight with metal case and a lot of batteries. So most of these things are just advancement in ability to tune properties of materials. And most of the properties of materials that they use are For example, dielectric. So it's a very, very good concept to understand. And as a physicist studying solid state physics, these are things we need to know. Take, for example, I'm an expert in solid state physics. Most of my research are based on properties of materials. So I study properties of materials specifically for industrial application. I compute optical properties of materials, magnetic properties of materials, and also try to look at the application in spectronic and and optoelectronic industry. So these are things we are going to be discussing. So if you have any question, you can call my attention, then I will respond to it. Are you with me?
Yes, sir.
Okay,
You
good.
can go on.
Okay, now, so most of these formula, we go through them one by one. If one is not clear to you, we try to look at how each of them have been derived. You know, one thing is that as a physicist, our mathematics should be good enough. If you look at this equation 1.11 now, this is mainly trying to compute a kind of a charge potential. So when you have two different charges at two different distance, so the difference between them, you can use them multiplying by the charge itself, you can compute the potential. So it's more or less like a dipole calculations. So and you can see the derivation of the formula. So we look at all these things, but it will be very good if you yourself at your own hand, you take your time to read through. So by the time we are discussing it, if you have any questions, it's very easy for you to ask the questions and responses can be shipping. One thing you have to put in mind is that there is nobody that knows it all. I myself am still learning. I can learn from you, you can also learn from me. So we discuss all this in the second, third, and I think second and third week, we should be able to cover all these things. And thereafter, we proceed to Unit 2. I think in Unit 2, we are going to be discussing most of the concept in Unit 2 is magnetism. So here, most of the things we are going to be dealing with is what is the concept of magnetism? That's what we're going to be discussing. And there is no how you talk about magnetism without looking at some of the types of magnetization or magnetic properties. So one of them is what we know as ferromagnetism, diamagnetism, and paramagnetism. So how do you identify that a material is ferromagnetic in nature? How do you know that a material is paramagnetic in nature? What relationship between paramagnetism and ferromagnetic in terms of susceptibility of the material? So all these concepts will guide us to have good knowledge of this aspect. We shall discuss all this, and hopefully I believe by the end of the 6 weeks, we should be in a better position to say, oh, when they talk about magnetic property of material, at least I know one or two things which I'm going to discuss. One thing I want you to know is that when you are reading this note, pay attention to permeability and susceptibility of paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and diamagnetic materials. It is a known fact that some of them, the susceptibility is 1, while some are 0. So pay attention to them when you are reading it. And we will discuss it in details also during our courses. Then if you look at the formula for magnetic susceptibility, which is 2.3, we have magnetic moment all over the magnetic field. So if you know the formula, if you are given a problem to solve, ability to extract parameters from the questions or problem, coupled with the formula, you'll be able to compute a numerical data that you can actually discuss as a physicist that, oh, this value fall within the range of so things. So automatically this materials is ferromagnetic in nature or is antiferromagnetic in nature. So at the end of the 6 weeks, we shall be moving into the 7th week. So there we'll be discussing the imperfection in solids. So that aspect is a very good area because if you look at this picture now, like I was telling you the other time, that the Pauli exclusive principle, you have spin up and spin down. So if you look at this now, look at this figure 2.4. So the ordering of the magnetic moment here now is up and down, meaning that there is pair. So as a physicist, the magnetic moment or the total magnetization of this system is equal to 0. Any antiferromagnetic material, the magnetic moment or the total magnetic moment must be 0, because it is half. If you have 2 and divide it by 2, I get me now, it will be 1. So 1 minus 1 will give you 0. But in case of ferromagnetism, all these pins, they all point into one direction. So mathematically, a ferromagnetic material must not have any 0 total magnetic moment. Are you getting me now? Are you with
Yes, sir.
me?
Yes, sir.
So these are concepts you need to put in your brain and your heart. If somebody wake you up, what can you say about ferromagnetism and antiferromagnetism? You should know that one of them, the total magnetization is equal to 0, and the other, the total magnetization is not equal to 0. Because in one case, there are pair of spin. One is pointing up, the other is pointing down. While in the other case, it's either all follow one direction or either going up or going down. So there is no pair. Hope I'm making sense.
Yes, sir.
So you can see there are series of ferric magnetic interest that belongs to group of compound. You have manganese, cobalt, nickel, copper, what is this? Magnesium rather, then the zinc, the cadmium, and the iron. This iron too, or a mixture of this. So we form a compound called ferrite. Then the magnetic resonance, like I told you, these are some of the techniques used to study some of these properties. You say electronic structure of single defect as revealed by the fine structure of absorption. If you use magnetic resonance to study defect in material, you have a kind of a plot, a graph. So very close to the Fermi level, you will see if there is a defect in material, you will see a kind of a shoot in the kind of a peak in the graph. So that shows that at that point, there is a kind of defect in that area. Because most in this part of the world we are more interested in theory, not experiments. So it becomes difficult for us to know how most of these instruments are being used. But nevertheless, there are theoretical concepts or theoretical theories and methodologies that we also use to study most of these things. So one of them is what we call density functional theory that we use to study this electronic structure of materials. So from there, if we compute what we know as density of state of the material, if there's a defect in the material, very close to the Fermi level, you will see a peak in the Fermi level. So that small peak you are noticing is as a result of defect in the structure. So these are some of the ways that we use to determine most of these concepts. There's another method called nuclear magnetic resonance. So we shall discuss this in details, and hopefully by the end of everything.
Excuse me, sir. You mentioned density functional theory. It's just to study what?
So we use density functional theories to study properties of materials, most especially from electronic point of view. You know, there is a concept in quantum physics. When you have many electrons, it is easy for us to compute the density of state of a single electron. Are you getting me now? But
Yes,
if
sir.
you want to compute the density of state of n electrons, it becomes difficult because at each point you compute the energy of the system. So the energy consists of both the kinetic energy and the potential energy. And we all know that electrons are bound inside the core. Are you getting me now? So ability to compute the potential energy in the core becomes difficult. So there's a theory that was developed in 1960, between 1916 and 1964 by a scientist called Kohn. So the theory is just around the concept of density functional theory. So it's a technique that I use in my research to study properties of materials. So, and they also use it in the chemistry world also. So This theory have tried to help us to solve that problem using a lot of approximation and perturbation concepts. So when you are doing your project, I think by the end of this semester, you should be getting set for your project, I think, or you have started already.
I've started already.
You started, okay, good. So it depends on the
Mine
area
is
you are
in
doing the research anyway.
Yes, sir. Actually, I'm studying education, physics education, not
Please
pure
educate.
physics.
Okay, that's good. At
Yes.
least if you want to do masters, you can still learn some of these things.
Okay.
Okay. So we discuss all this together, and finally we move to the last part of the course, which has to do with crystal imperfections, solids imperfections, which is a very good concept in physics. In our days when we were young, we don't know much of this. We just see it as abstract. But when we venture into research, we realize that most of these things has a lot of applications. And today we are using them. So if you look at the content, we have crystalline defect. Here we'll be talking about zero dimensional, which is called point defect. So then one dimensional, when you have a kind of atoms arranged in an array, then you not distort the directions. So what will happen to it? These are things we are going to be looking into in this place. Then we discuss them in this case and try to figure out one or two things. So if you have questions, you can ask me questions. Any questions?
From my hand, not at all, sir.
Not at all. Okay, good. I think we have another student in the house.
Greetings, sir.
Yeah, you are welcome, my brother. How are you?
Fine, sir. I'm also physics education from Port Harcourt Center.
Okay, that's good. You are welcome on board.
Thank you, sir.
Oh. I believe
Okay, I've started.
You want to say something?
Yes, sir. I've started going through the materials.
Okay.
I'm actually still at the first unit. I'm almost done with it.
Okay.
The computation of this minus Q and plus Q, where we have Q plus Q over 2 and minus Q over 2 as the distance from X. That analysis, is this something we're going to look at? It's not quite clear for me.
What page is that?
That should be working into soft copy. That's the first unit, unit 1, sir. The one that has that triangle.
Okay. Yes, that is where they compute the potential of 2-point charges.
Okay.
You are referring to this, this place?
Yes, sir.
Okay,
yes, sir.
Good. So what exactly is not clear to you here?
The distance from the origin X, we have minus Q over 2 on one end, and then we have plus Q over 2. This analysis, is this something we will look at later?
Minus Q over 2. I'm not seeing what you are talking about here. Are you referring to this D over 2? This is not Q.
Hello, sir.
I'm with you.
Okay.
D over 2. Are you referring to this place?
Yes, sir. Yes, sir.
Yeah.
Yes, sir. I say in a subsequent class, are we going to look at this analysis?
Everything. We will discuss everything in details. Don't worry.
Okay, sir.
This is just a kind of an introduction class where we interact with each other to know what we are going to be discussing and things we are going to concentrate on. I get him now. By next week, we start the class in details. Then we start treating each of the units one after the other. But at this point, don't be disturbed with this concept. It's just like you have D. The total length is D. I get him now. If the total length is D, so let's assume that we are at this point now, origin.
Like the midpoint.
The midpoint. So it is D divided by 2.
Okay.
So let's assume that you are using a Cartesian coordinate to describe it. So in that case, you have X. I get him now. So S towards positive and S towards negative. I get him now. So
Yes.
x toward positive now, we take half of the distance. That is why you have d over 2 positive.
Okay.
So x towards negative, that is why you have minus d over 2.
Okay.
Are you okay with that
Yes.
concept?
Yes, sir.
So if you take absolute of these two now, that is d over 2 absolute minus d over 2 absolute, and you add them together, you get d,
Okay.
which
Yes.
is the distance. Is it clear?
Yes, sir.
Okay. So don't worry, we also discuss all these things together in the next class in detail by the time we get to that point.
Okay. Thank you, sir.
You're welcome. Any other question? Elijah CD cards.
No, sir.
Okay, good. So I think we're almost done for just a kind of brief introduction to what we are going to be discussing. So if you have any questions, you are free to contact me by mail. You all have my mail. I think so.
Yes,
Yes,
sir.
sir.
Yeah, so if you have any questions, maybe you read something and you don't understand, feel free to send mail to me. I'm always available. I will try my best to respond. So by
Yes.
next week, we start the class in details and we start discussing. But before then, I will have done a lot of things behind the scene by trying to break down the lecture notes into something that you can actually pick points, and with the point you can understand what is there. Then I'll send a kind of a video to you people to read through, and by the time we have the main class, we can actually exchange ideas and ask questions and one or two things. So thank you for coming. I would like to stop the class here now. If you don't have any
Thank you
questions,
very much, sir. Thank you for
you're
your time.
welcome. So
Thank you, sir.
I will send this video to our course page, so you are free to download it at any time and make use of it.
Okay, sir.